Everyone. Before we can do some calculations with the weak interaction, right, we need to figure out the W boson propagator because that's going to be different from the gluon and the photon. And this is section 11.5 in Thomson. Let's see. I think it does go a little bit deeper than just deriving the propagator. It also does this thing called the Fermi theory, which is actually very useful. And I want to make sure to show you guys this because other people are going to use it. So if you don't know about the Fermi approximation, then you would not know what they're talking about. So it's actually important just from a historical perspective that we talk about this, okay? So since the W boson has a mass, right, the propagator for this weak interaction, right, it's going to be proportional to, instead of just Q squared, 1 over Q squared, right, it's going to be 1 over Q squared minus the mass of the W boson square, right? The mass of the W boson is like about 80 GeV. So this is going to be a substantial number, right? Until you get to extremely high energy or extremely high Q squared. Okay. And the mass of the boson, of the W boson, also adds a third polarization, the longitudinal polarization. So remember that electromagnetic wave photons, right, can only have has vertical or only horizontal polarization, right? That's because the photon is massless. But if you have a massive wave, it can also have a longitudinal, which is along the direction of the propagation of the wave. Okay, so it has a third polarization, and this third polarization adds a factor of q nu divided by the mass of the W boson square. Okay, if you multiply these two together, you get this complicated propagator, and this is actually the real propagator for the weak interaction. Okay, we have this minus I just so we can make things Hermitian. And then you have this Q squared minus M of the mass of the boson, W boson square. And then you have this polarization factor. Okay, so since the mass of the W boson is much bigger than the Q squared usually, right, this equation can actually get reduced because this Q mu Q nu multiplied together is going to be fairly small. Okay, so what you can do is that you basically just approximate this term to be approximately 0. Okay, and that way the weak force propagator is basically just going to be negative Ig mu nu divided by Q squared minus the mass of the W boson square. And this is typically what you're going to see in most cases when you're doing calculations for the weak force. In the next section, we're going to do one more approximation, but this is the reason. This is the W boson propagator you will typically use. Okay. What this allows us to do is basically calculate things like a D quark. Let me just draw this little drawing. Right. A D quark. Oh, there's a Feynman diagram right here. I need to draw it. Okay. A D quark, right, changing into an up quark through interacting, let's say, with a electron neutrino and an electron this way. Okay, this is actually how a neutron decays into the proton. Remember, a neutron has 2 valence down quark and 1 up quark. Okay, in order for this to convert into a proton, right, one of these quarks has to change into a up quark, right? And this is a process that happens. And then during this process, basically an electron and an electron neutrino jumps out. Okay, but that's the idea for this decay. Okay, so if you were to follow the full Feynman rules in order to do this, okay, we're not going to go through everything. What happened is that you will have, so this is psi 2, which is this guy. Oh yeah. So let's just do it once. We're not going to calculate this because it's so complicated. Okay, so you have psi 3 right? Which is, you're starting from this point, right? And then you reach the weak vertex, right? Remember the weak vertex has this factor of 1/2 gamma mu times 1 minus gamma 5, which is the V minus A aspects of the weak interaction. Okay, and then now you reach gamma psi 1, which is the incoming electron neutrino. And then now you have this vertex, this propagator. That's where this comes from. Okay, right, that's on this side. And then similarly, right over here on the quark side, right, you have something very similar where you have psi 4, 1 minus 1/2 gamma nu times 1 minus gamma 5 times psi 2, and then you have these two factors of the weak coupling constant to basically calculate what the magnitude of this matrix element is. Okay, we're not going to do this, at least not yet. I'm not sure we're going to do this next chapter or not, actually. Okay, we're going to do a very simplification of this in order to calculate a pion decaying. Okay, right. But before we do that, what we want to do is actually introduce to you an approximation. Okay, so this process here is actually known as a beta decay because the electron used to be called beta particle. Okay, and basically what will happen is that you have a neutron sitting here, and then what happened, 16 minutes later on average, it turns into a proton plus an electron. Okay, technically it also turns into there's a neutrino, anti-neutrino escaping, but we don't actually measure these. We didn't even know they existed until like the 1960s, right? But we know about protons and electrons, and that's why we're actually able to measure this. This was actually first observed in 1896, right, by Marie Curie. I don't think there's an S there. When she was observing the thorium, and also Henri Becquerel in uranium. So this is, 50 years before we even understand the weak interaction. Okay. And during these 50 years, people were trying to figure out what the hell's going on here. I don't understand how this is happening, right? What Enrico Fermi came up with is basically an approximation method to explain the beta decay. Okay, so how does he do this? Okay, so let's go back up here, right? We have this propagator here, right? That's g mu nu, and then divided by q squared minus m of the mass of the w squared, right? During these neutron decays, the q squared is going to be very small because the mass difference between the neutron and the proton is so small, it's just giving off a little bit of energy during being exchanged between them. So q squared is very small. So in that case, right, since q squared is very small, then you know that it's actually going to be much smaller than the mass of the w, which people didn't know what it was at that time also, but Fermi is also going to approximate this. Okay, but what happened is that basically the propagator can be turned into just g mu nu divided by the mass of the w square with an I in front of it. Okay, and what this does is that it basically turns this Feynman diagram into what's known as a 4-point diagram, where you just have a quark coming in, a quark coming out, which allows you for the neutron to decay into a proton, and then giving you an electron and the neutrinos, the incoming particle, which if you flip the direction of it, it turns into an anti-neutrino going out. So a neutrino coming in is equivalent to an anti-neutrino going out of a vertex. Okay, in this case, the Lorentz invariant matrix element can be calculated simply by, with this 4-point diagram, as just being proportional to these two currents, right? The up quark, down quark, and the neutrino currents, g mu nu. And Fermi decided, oh, well, this is going to be proportional to some constant, and since it's Enrico Fermi, he's going to call it the Fermi constant. Okay. The Fermi constant is actually the actual value. These were being measured because, right, you can measure the decay rate of neutrons. And by just measuring the decay rate of neutrons, you actually can able to experimentally figure out that the Fermi constant is actually about 1 times 10 to the negative 5 with a unit of inverse GeV square. Okay. It is actually related to the weak coupling constant. The weak coupling constant squared divided by 8, and then the mass of the W is actually equal to the the Fermi constant divided by the square root 2. And this square root 2 is just an historical artifact that Fermi put in order to do his calculations. Okay, so this can not just be measured by the neutron decay into protons, but can also be measured by muon decay into electrons. Okay, so one of the first things we learn in modern physics is that muons are not stable. So you have a muon, and it can decay into basically, I think usually it's like this, right? It decays into an electron. Okay, in order to conserve the number of electronness, you have to have an anti-electron coming in. Actually, let me draw the full decay. Okay, but what Fermi does is that he just squish the W bosons away. This turns into a muon neutrino, right? This is a electron anti-neutrino. Okay, and this is your electron. And what Fermi does is just squish this together into a 4-point diagram. So what you have here is you have a muon coming in, and then you have a muon neutrino coming out, and then you have an anti-electron neutrino coming out, and you have an electron coming out. Okay, we draw the arrows the right direction so that, right, so we actually are tracking the particleness. So this is the 4-point diagram that Fermi is calculating. Okay, and you can, we're going to show this in much more detail with the pion. What's going to happen is that you're going to find a result where it's proportional to the Fermi constant square, okay, times the mass of the muon to the 5th power, where like all three of these things are going to be just assumed to be massless, okay, and there's this factor of 192 on the bottom and pi to the 3rd. So if you know the mass of the muon, which is 0.105658 blah blah GeV, okay, and you measure the lifetime of the muon. So if you get a bunch of muons and you figure out what his lifetime is, you can actually calculate, right, what G Fermi is, because right now you have this number, well, you know what pi is, you know what 192 is, okay. So G Fermi, right, is actually calculated to be, right, exactly about 1.17 times 10 to the negative 5 with units of inverse GeV squared. Okay. With this, right, since you have this relationship between G Fermi and the weak interaction, and if you know the mass of the W boson, okay, you can actually also calculate the weak coupling constant, GW. Okay, in fact, what we're going to do here is we're actually going to calculate GW squared divided by 4 pi, which is equal to alpha W, which is the alpha coupling constant, and we're going to compare this to the electromagnetic one. If you actually plug all these numbers in, what happens is that alpha W is actually 1/30. Okay, right? Comparing this to the electromagnetic force, right, which is 1/137, you would think that the weak interaction is actually stronger, right? Then why do we call it the weak interaction? Okay, the reason the weak interaction is weak is because the W boson has a mass of 80 GeV. This suppresses the interaction rate. In fact, this suppresses to the interaction rate such that basically the the weak interaction coupling constant alpha W effective is basically about 10 to the minus 4. And this is what I think in the beginning of the textbook, Thompson was talking about when he's talking about the weak coupling constant actually being stronger than electromagnetic. The problem is that whenever you're coupling these things, you also have this 1 over mass of the W boson square in your matrix elements, and therefore it actually suppresses that number, okay? Because, right, for the gluon and the photon for QCD and QED, right, the mass of the gauge boson is actually 0, so therefore it's actually Q squared that matters, not the mass, okay? In this case, since the mass of the W boson is so large, it's actually what suppresses the weak interaction instead, okay? All right, I think that's it for this one, and then we will talk about pion decay next.